right. Hello, everyone, and welcome to the second day of the conference. Today's first speaker is CTO at IO Interactive. He oversees development of both Hitman and the Glacier 2 engine. Please welcome Maurizio de Pascale.
Hi guys, thank you. So my name is Maurizio, I'm the CTO at IO. I spend most of my day as a technical director on the Hitman project. And today I want to give you an intro to two of the major systems in our engine. So the resource system and the entity system. If we have time, I'll try to cover a little bit of what we plan to do in the future with this tech. So a little bit of history. Glacier 2 is IO in-house technology. The engine was written over the past 10 years, practically from scratch. And its design was heavily influenced by the PS3 and 360 generation. But overall, the architecture is quite sound, so it was pretty easy to port it to PlayStation 4 and current generation of consoles. And the engine is heavily multi-threaded, so it was kind of natural. IO used to be part of Square Enix. So a few years ago, the engine was also adopted as technology by a sister studio, IDs Montreal. So the engine has been used to ship multiple titles from different studios, and it's currently in continuous development, and it's being used for future titles, both at IO and IDs Montreal. Now that IO and Square Enix have parted ways, of course, IDs Montreal it's on their own fork, on their own branch of the engine. So back when we started designing G2, the main cost for production and the main bottleneck was content creation. So when designing a new engine, our primary focus was really the content creation workflow. So we focused on three pillars, which was what you see is what you get, and live editing while the game is running, hot reloading of everything at any time, and trying to reduce as much as possible human steps and human mistakes by having an asset pipeline that will be as automated as possible. Now, let's begin by the resource system, which plays a massive role in the engine. So I'll have to begin with a couple of boring slides to introduce some terms, but it will make it easier to understand the rest of the talk, because I'm going to use these words over and over and over. So for us, a resource is any type of data that you can load. Basically, just think of a file or a subsection of a file. We call resource ID a unique identifier for one of these resources. And we use this weird name packing for compressing texture, converting formats, changing NDNS. Other engines use the word cooking assets or compiling resources or building data. You get the gist of it. And very importantly, central to our asset system is the concept of a resource dependency. So resource dependencies are the set of resources needed to generate another resource. Okay? So as an example, think of the source code is something that you use to produce a binary. So it's a dependency for the executable that you're generating. Now, we distinguish between two types of resources that we call source resources and derived resources. A source resource is something created by a human through a DCC tool or through one of our custom editors. A derived resources, on the other hand, is something that is automatically built by the build system by just applying certain transformation to a bunch of input resources. They can be source resources or they can be other derived resources. One of the important points is that derived resources are completely volatile. They can be deleted and they will be regenerated. And very importantly, this full process is completely deterministic, meaning they will be regenerated. Given the same input, you will always generate exactly the same output. Now, in practice, it's very hard to enforce determinism or to guarantee determinism, but we have a lot of system in place to basically detect sources of non-determinism and remove them from the system. Now, dependencies between resources, they kind of define a graph. Okay, so on the far left here, we have all the source resources. Some of these exist just because they've been created, even though they're not actually used. And then you have some intermediate resources. And then finally, on the far right, you have the assets that the engine or other tools will actually eventually load. Now, the concept is that basically by backtracking in this graph, you can always understand what's needed to build, what things you need to build to achieve what the engine wants to load. Okay? And one important key is that this graph is really not fixed, right? Because during development, people are submitting new files, they are changing the way the system works. So this graph is constantly evolving and constantly changing. But one key point is that given the set of source resources, because each one of these transformation is completely deterministic, then the rest of the graph is fully determined, okay? So if you fix this column, then everything else is fixed as well, okay? So you can basically think of packing, producing this by these two inputs as applying a pure function in a functional language, okay? Now, dependencies can be classified in two types, static and dynamic dependencies. So a static dependency is something that doesn't really depend on the content of the actual file, something that you just know. An example, when you're packing a texture in our engine, you will always depend on a global file with compression settings. Okay, so no matter what pixels are actually in the texture, you know that you're going to need this file to read the settings for compression. Dynamic dependencies, on the other hand, is something that you can actually only discover while doing the actual packing processing. I mean, once again, an example to give you an idea of dynamic dependencies is header files when compiling a binary, right? You will only figure out what headers you actually need to include when you start parsing the main source file, right? You will find the include directives, and you will know what other things are actually needed and what needs to be brought in. One thing that it's important is that in our system, there's always, in the graph that I showed before, there's always at least one implicit static dependency. I'll explain why a little bit later when we talk about our resource IDs. But the key point there is that basically there's no node in that graph that cannot be connected backward, which basically means that no matter what the engine or the tools are asking, the system is always able to backtrack and eventually rebuild the full subgraph that it's needed to produce that resource. Okay, so from the point of view of files, this is actually how our asset pipeline looks like. So on this left, basically we have raw DCC files, things that artists use, 3D Studio Max, Photoshop, and so forth. They get exported, sometimes manually, sometimes also in a kind of automatic way, into the source resources that I've described so far. Source resources, they're generally stored in a platform-independent format. Quite commonly, they are in a human-readable format, and they are generally they're meant to be easy to use for tools and for human to debug. Then the resource system kicks in and basically builds everything else as needed on demand. And so derived resources, they're generally platform-specific, even though this is less of an issue for this generation of consoles. They're generally binary and compressed files that are basically optimized for fast loading in the engine or for easy use from the engine more than for tools or human consumption. Now, these three conceptual stages for assets that assets go through in our engine, they kind of map to literally three folders on disk that we call construction, assembly, and runtime. So the construction folder is where we store all the raw DCC files. This folder is mapped in Perforce, and it's usually synced only by artists. Actually, they only sync a subset of it because it's fairly large. On the Hitman project, we're probably talking around north of 3 terabytes of data for the construction folder. The second folder, which is actually the core of our system, is what we call the assembly folder. The assembly folder contains all source resources. It's stored in Perforce, and the usual pattern is for everyone working on the project to get latest on that folder. And as I described before, since this folder contains all source assets, the state of this folder describes the entire graph, basically what you will be loading. Okay, so the key point is that I can sync that folder and then remove the plug from my computer, the network cable from my computer, and my computer will be able to fully rebuild the entire game exactly in the same way as anyone else will could do on their own machine. Finally, we have the runtime folder that contains all the derived resource. It's basically, you could call it a local cache, pretty much. And it's completely volatile. We can delete it part of it. They will just automatically be regenerated as needed. And as I mentioned, this is a local folder only. There's no need to store these files in Perforce because they can be regenerated exactly in the same way automatically. To give you, again, an idea of size, the assembly folder comes around 1 million resources, 10 million, counting all revision, and I think it's around 600 gigabytes or something like that. Now, this is how the system works. Now, the main duty of the systems for its clients is basically to provide ready-to-use assets to the client processes. Okay, so the engine, the editor, the various tools in our ecosystem, they will ask for assets that they want to load and use, and it's the responsibility of the resource systems to make sure that those files are up to date and ready to be used. And it does this by packing assets on demand, so only when they're needed. This is quite different from many other engines that usually do the packing or the cooking steps at import time. So when you're dragging something into the engine for the first time, they get processed. In G2, there's no initial step. When you're adding resources, they're just added, and they will be processed only when they're actually needed. Okay? And the resource system also supports hot reloading for the engine by basically monitoring the state of these assets on disk and intercepting changes to this file from content creators and notifying clients that have loaded assets so that they can basically hot reload. And react to changes. And finally, the resource system also maintains a database of information about assets because since it's the single central place that sees all transformation to assets, it's very handy and convenient to intercept metadata there and make sure that metadata about assets and the actual assets are always exactly in sync. Now, as I mentioned before, packing is what we call the process of transforming assets between different formats in an engine-ready, pretty much, format. And these are some of the common use cases: compressing texture, converting handiness, computing bounding volume of hierarchies, and so forth. And in our resource system, this process is completely data-driven. So it's not hard-coded as part of the system, but it's controlled by a configuration file that contains what we call build rules. A build rule is basically, it's a way of defining the transformation that you can apply to a source type to generate a given destination type. Okay? This is an example of a build rule. The key points on this slide are actually these two lines, so the target extension and the source extension tags. And this is basically saying if you want to generate a collision geometry out of a standard visual meshes, this is the code that you have to run. This is the transformation that you need to apply. Up here, we specify which platform this rule applies to. Again, on previous generation, it was common to have different rules. These days, we're mostly using platform-independent rules. And we also specify these two lines here, basically injecting in the dependency graph some static dependencies. Here we're basically saying every time you're generating a collision geometry from a visual geometry, you have an implicit static dependency on the version of your physics system, because the physics system is actually what is gonna calculate the apply basically the transformation. And of course, every single resource pretty much depends on the format of the header. So this is how the dependency graph is actually defined and what are the rules to basically build it. The system basically always knows how to build things by just moving along these lines. So let's actually see how, in practice, on-demand build works in our system in a step-by-step way. So it begins with the engine or any other tool issuing a request to load something. And then the resource system will just walk backwards and figure out what are the resources that are needed to generate this one, and what are the resources needed to generate the intermediate steps in between. Once it reaches source resources, it knows that these are basically the leaves in this graph, and it can just start applying those build rules, matching those build rules, and applying the packing process to generate the resources in the intermediate resources. So the first one will be generated, and then from this one, the one that was actually needed would be generated. Once the resource that was requested is created, then the engine will be notified that the resource is ready to use and can be loaded in memory. Okay? Now, pretty much the same principle is used to support hot reloading. So once again, it begins with the engine or any other tool asking the resource system to monitor a resource. And actually, in general, this happens as an atomic operation. So you're really saying load and monitor, okay? Because you don't want to miss changes to the asset between your initial load and then the request to monitor. So we do this in a single operation. So once again, the engine is telling us, hey, I want to know if something happens to that asset because I loaded it before. Then your artist is working, the game is running, and at a certain point he changes a file on disk. He presses Ctrl S in 3D Studio Max. Our Max plugins automatically export this into a source resource, and now a source resource has changed on disk. So now what happens is that the resource system sees that these things has changed, and it automatically marks everything that had this as a dependency as potentially out of date. So these two resources are now out of date. It will then move forward and try to rebuild one of these things that I've changed. And once it noticed that, yes, this resource actually has to be repacked, and it will be repacked into something that is different than it was before, because one of its input has actually changed. And then it will, in turn, bubble up this, will kind of propagate this fact that now new resources are out of date. Okay, so eventually the resource that was being monitored will also be regenerated automatically, and the asset system will notify the engine, your resource has changed, you can now proceed to hot reload that asset. Okay, so a new version of that resource is available for you to load in memory. Now, that was basically how it works. Now let's see what are the pieces to build this system. So on the right, we kind of have the client processes, so our engine, our editor, engine running on a console. So I'm using this convention of using rounded boxes for applications and rectangles for potentially a different machine. So the build system, the asset system is basically running locally to the same PC that you're actually using, but it can serve other machines or other consoles, and I'll cover this part later on. But basically, these two up here are the main part in which the asset system is split. So on the left, all those small boxes are what we call packers. The idea is that the resource system is completely data-driven and pretty much content agnostic. All it cares about are dependencies, right? To do the actual work of transforming, we use a bunch of software modules that basically contain the content-specific code to do the transformation. Basically, an object or a class that knows how to generate a collision geometry, a piece of code that knows how to produce a texture, and so forth. So that the system can be extended very easily by just adding these new binaries and adding the required build rules. And most of our packers are in C#, and we use C++ mostly for legacy code, or in cases where we do the same transformation, both runtime in the engine and offline. And of course, when we need to use libraries that are provided by middleware vendors. We also support command line tools, but I'm not even sure that's used anymore, to be honest. Now, packers, they're kind of something that the resource system uses, and they run in a special environment. The idea here is basically we want to protect the build system from errors in these packers, right? Just because a texture is failing to pack and that specific code is crashing, you don't want to bring down or stop the entire processing. So what we do there is that packers are run as external processes. A new process is started up, it executes just that piece of code that needs to do, and then it's brought down. Now, this is nice on paper, but in practice, there's a lot of overhead from starting packers all the time. So what we do is that generally we use a couple of what we call persistent packers, which are basically host processes for packers that are then loaded dynamically. Okay, and we use this kind of to save on the startup overhead, and for certain specific types to avoid reloading from disk over and over the same type of data. So all packers that are processing meshes, they're basically hosted by a single packer, so there's a single cache that is exploited by all of them. Now, I mentioned that the resource server is pretty much that other big box is the core of the system. So it pretty much implements all functionality that the resource system exposes as a wall. So it provides assets to client applications. It makes sure that assets are up to date and monitor changes and maintains the database. And again, the key point is, despite the name, this is a local running application. It's not a remote server. It's on your machine. You can take it on on your laptop with you, pretty much. The name is misleading because server always gives the idea that something is remote, and maybe we should call it in a different way, maybe service or something like that. Anyway, when it comes to the internals of the resource server represents each request for a resource with a final state machine. And the state machine will basically transition to different states. So it will extract the dependencies, recursively check that the dependencies are up to date, talk to the cache to see if the things is already ready, pack or download locally, upload, and so forth. Each one of these steps is very small, and it's completely atomic. It can't be interrupted. And all I/O operation, talking to the cache or doing the actual processing, is basically done in between transition. And this basically allows the resource request to be held in a bunch of priority queue, which basically means that we can reshuffle priorities on demand as needed. And a typical use case is that you will start loading your level, no data is there, so the system starts preparing everything for you. And then you click on a specific object that you want to interact with right away. And the editor will ask the resource server to raise the priority for that object. So no matter what was being done, even if many of those assets might have been halfway during the processing, the object that you have selected will have priority. So it will be completed before everyone else. And of course, the bubbling up of priorities is propagated to dependencies to ensure that it works recursively, pretty much. And it's heavily multi-threaded internally. It's not a big deal these days, but it kind of was 10 years ago when it was originally made. We have a GUI for the resource server, even though you're not even supposed to use it. To be honest, it's mostly a debugging tool to see if something is actually going wrong. So for each resource that is being packed, it can tell you if there were errors, if there were warnings. You will have the full log from the packing process, and quite conveniently, we have this run and break button down there, which allows you to basically, if something fails, you can rerun, and it will execute just that process, and it will automatically attach a debugger. So you can single step and find out why your packing process crashed or failed. Now, as I mentioned, the resource server is really not meant to be used by humans. It's pretty much for other programs to ask for assets. So all its functionalities are available through a native API, which is available in both C++ and C#. And so this API basically contains method to load resource, to monitor resource, to retrieve information about the resource, to do database queries, and of course to create new resources. Even creation of resources always goes through the resource server, so that it always knows when something changes and when something new appears. Now, the resource server runs locally, meaning each machine is pretty much able to rebuild everything that it needs, but that will also be a waste if everyone has to repack over and over the same file on each machine. So what we do is that we use a central server as a cache, and this is called, it's it's running an application that we call the resource cache server, and it caches derived resources for the entire team across every branch. Okay, it's not tied to a specific branch. And the key there is that the resource cache server maintains multiple version of the same resources and maintains information on all the dependencies and the MD5 of those dependencies that were used to generate. So the way the communication protocol works is something like, okay, I'm a resource server. I will ask the cache server, hey, I need resource X. And the cache server will reply back, okay, out of the multiple version of X that I have, I think they can be done, they can be generated by using A, B, C, and maybe D or E as input. Which version of A do you have? Which version of B do you have? Which version do you have of those stuff? The resource server will reply back, yeah, I have this version of A, this version of B, this version of C. I don't have D, but I also have a version of E. By using this ping-ponging, the cache server will basically tell you, okay, I have the file, exactly the file that you need, or it will tell you, I don't have that file. It's your responsibility to produce it and then to upload it back to me. Now, I mentioned resource IDs. Each resource has a unique name, can be uniquely identified through an identifier. And we use a somewhat different format for source resources and derived resources. For source resources, our ID is basically, it's a string. And as you can see, it's pretty much just a glorified path, right? This is saying, get that file from the assembly folder. It's actually get that sub file from that file in the assembly folder. For derived resource IDs, the resource ID actually implicitly describes a static dependency, because the format is in square bracket the source of the input. Source here is kind of misleading. The input that you want to process, and the platform will define the transformation that you want to apply. So basically here, by matching this extension and this extension, the asset system will know that, well, I need to run the packer that is able to produce PC-specific textures out of a diffuse platform-independent texture. Okay, so this is the way every time you're asking for something, that's really kind of implicitly pointing backward, and that's how that graph is guaranteed to always have at least a connection. Now, human-readable strings are nice for humans, but they're terrible for machines. So on the engine, we actually use a different representation. We use a 64-bit integer that we call a runtime resource ID. And this number is basically generated by purely hashing the string of the resource ID. We use a stable hashing function, so given the same input, you will always get the same number, pretty much. And we've written plugins for Visual Studio, and all our login tools, they are aware of this translation. So pretty much when using the engine, you will never see the number, even though the engine is using numbers under the hood. You will see numbers pretty much only if you are debugging, literally, these few things here. So, so far, I've kind of covered the tooling part of the resource systems. Now I'll give you a little bit more details about the runtime part, what basically happens inside the engine. So all of our resources, pretty standard, have a default structure, a standard format. Okay, so we have a header, and then there's the actually payload, which contains the data, and the metadata contains a list of what we call referenced resources. And in G2, it's important to distinguish that references and dependencies are actually two very distinct concepts. So we say that A references B, that an asset A references an asset B, if it needs to load that asset at runtime. Basically, if that asset needs to be in memory before. Okay, an example is that that material can be packed even without the texture that it's using. But before it can be used in memory, that texture needs to be loaded. Okay, so the idea is that when the engine is loading something, it can look at this list of references, and it can automatically guarantee that everything that also going to be needed will be loaded in memory and installed. Dependencies, on the other hand, they are only used by the build system. They're not used by the engine at all. There's no use case for them in the engine. Last one, this is the way hot reloading is actually implemented in the engine. What we do is that we always use a smart pointer to deal with data instead of using a raw pointer to the data. And the trick here is that the pointer doesn't point to the actual data, but points always to an intermediate stub, a small struct that contains a ref count, the type of resources, the resource ID, some additional flags, and so forth. So when the resource system notifies the engine that a new version of that same asset is available, what we do is that we create a new stub, and it gets linked, okay? Then the new data will be loaded in the background. Then at a very control point in the engine loop, resource pointers could be rebinded, okay? Rebinding means that you will just point yourself to the latest stub in the chain. And then later on, once all resource pointers are moved to the latest chain, the ref count will go to 0, and the engine will just unload things from memory. Okay? So that was an overview of the resource system. Now I'll give you a brief overview of the entity system and how these two systems works together. So entities are building blocks in G2. They're pretty similar to game objects in many other engines. But the model we use for entities is a little bit more general than commonly seen. We use entities to model these three things all at the same time. So we use entity to model instances, a door, an instance on a specific type. We use entity to model composition, a room with multiple things, a box with multiple objects inside. And we use entities to model the flow of events. A door was opened, an alarm needs to be triggered. And entities are pretty much compiled into native objects, so they run exactly as if you were writing them as C++, but additionally we support aspect-oriented design through something that we call aspects that I'll cover in a bit. So this is a minimal error word of how a couple of entities look in our engine. So there's a box to represent them, and when bar will time out, foo will actually start. That's how we model the flow of events. Now, entities have properties, and you should think of properties more than C++ field. You should think of C# properties, meaning they do a little bit more than just holding data. They can have attributes, so we can specify and control the behavior of these things. And in particular, you can define what we call a change handler for a property, which is basically it's a piece of code that is responsible to reacting to changes in that property. Then we have these pins, which are basically used for events, as we've seen before. So output pins are basically events that an entity can raise, and input pins are event handler that an entity can use to react to events. And they carry a single optional type argument. Now, the base entities that we use as building blocks in G2, the most simple ones, they're pretty much written in C++. This is an example of a camera-related entity. And we basically use a markup language through macros to basically extend the semantic of C++. So the top there, a bunch of macros to basically specify, not visible, to specify the input and output pins. And here there's a couple of fields that have been extended to be properties. So they have attributes, and this one, for instance, has a change handler that will do something when the blend is actually set. We have a small application that we call the property parser, which is a manual written C# parser for C++ headers. And it basically interprets those tags, and it also understands the structure of C++ objects. And it does two things. It generates two type of content. It generates C++ source files, mostly with templates and initialization function that we then link into the engine. But the interesting part is that we also generate exactly the same information in a data-only format. This basically means that we can do transformation or use entities even when the engine is not running. Okay, so our engine and our editor, they run as two separate applications. One is full in C#, the other is full in C++. And basically, we can edit the game by just running the editor. We don't need the engine to be running. Okay, so we never get in those crazy circle of that where your engine doesn't compile anymore and you can't even fix it because you're basically stuck with it. Okay, so basically the editor doesn't really run in engine to exist. templates, templated entities is basically our way of composing entities. And so you can recursively compose other templates or C++ entities, and then you can decide what you want to expose on the parent, which pins, what properties you want to expose on the parent. So it's a way of creating something complex out of smaller items. This is a small video of the graph view in action, and I mean, one comment here is that basically we use these composite entities also as a grouping mechanism, pretty much. It's pretty efficient, so there's no point in making something that it's purely for grouping. The resource pointer that I mentioned before. So the resource pointer can be used by C++ code, but can also be used as a property on an entity. So it can be set up basically in the property editor on the editor, and it basically represents the easiest way to use resources for level designers, because once you have a resource pointer on an entity, the system will make sure that that resource is automatically loaded for you and will be there when your entity is initialized or when the entity is fully loaded. Okay, and then you can specify a change handler to react to changes in that resource. So if you have an MPC and you have a mesh, you will just put a change handler there, and if an artist changes the mesh for the MPC, you have a chance to run that code that deals with that modification. Okay. Aspects, as I mentioned before. So aspects is basically, it's another way in which we compose multiple entities into one. The main difference with templates is that when you have a template and you're putting sub-entities inside it, they have a different identity. So the children and the parent, they actually are two different things, right? So an equal operator will basically return false. Aspect is a way of merging entities together in such a way they end up with a single identity. It's pretty much imagine like, taking a bunch of C++ object and then just writing a new C++ object that has all the methods, all the fields, all the properties merged together. But now it's just a single thing. Okay? And an example is the way we do MPC is that we take a skinned actor and then we add an AI aspect to it, and now it's basically part of the AI system. And if we want that stuff to interact with the physics systems, we just add physical aspects. So it's basically our way of doing components in other engines. The life cycle for entities is pretty standard. This is actually a simplified version of it. There's a little bit more stages. But the two of the points that are worth mentioning is that entities, they get notified when you start and stop things in the editor. So they can be a little bit more editor friendly and behave differently when they are in the editor, even though we recommend not to. And a good point is that the initialization order of entities is always fully deterministic, even in the presence of a loop, a reference loop. So we try to teach designers to not have entities referencing an entity, and closing the circle. But then we gave up because they kept doing so. So the way the system works is that it automatically identifies the loops. It breaks the loops by removing one of the cycle, initializes everything else in reverse order of referencing, and then it basically piggybacks with the hot reloading by resetting the link that was removed. And since the system is designed to cope with changes, it will be able to basically restore the correct state for all the entities in the loop. This is a video showing how we do debugging, because pretty much our entity system is a visual programming language. I don't know if it's Turing complete, but they can do pretty crazy stuff with it. So we try to provide good enough tools for debugging. So there's extensive logging, there's visualization of what's going on. We display what value are flowing, what main values are being seen by entities, and we can place breakpoints, which is super useful, pretty much. There we go. I don't even know how we lived before getting this feature. Memory-wise, as I said before, the G2 system was mostly designed during the PS3 era, so we were fairly obsessed with memory. So in terms of overhead, entities are kind of lightweight. There's basically just an additional pointer pointing to some metadata information, and then there's the usual C++ vtable pointer. At a certain point, we even did some experiments to combine the two, but it wasn't worth it, just to made it harder to debug stuff. And all the type information are based on offset, not on pointers, meaning they can be trivially reused not only between instances, but also between types and aspects. Now, instantiation of entities and dynamically creating entities. We can dynamically create entities, of course, and the key point here is that each entity gets allocated with a single memory allocation. And that applies to any type of entity, even for templated entities. So the catch here is that when we're making a level can basically technically be made. It's just an entity. It's just a composite entity that contains multiple sections, and then those sections contains multiple geometries, multiple NPC, and so forth. And all of this is just a single entity, meaning when it will go into the engine, it will basically be a single allocation and then a single mem copy. We pack our levels by basically producing a memory-ready version of that data. So the data is basically just mem copied, and then we just patch the pointers pretty much. And of course, we support placement constructing of entities. So if you have a specific need, you can do the manual memory management yourself, but it's not generally it's generally something that we don't do. Now, Bricks. Bricks is a terrible name, but it's basically our layering system. I think it's a terrible name because Bricks gives the idea of something that can be added, but in reality, we can use Bricks to add, remove, or just change everything, pretty much, entity, properties, and pin connection from existing bricks. So this is basically our way of making our content kind of modular. So the general idea is that one level will have a base bricks that contains the static geometry. Then there will be another bricks on top that is adding lighting condition in a specific time of the day. Then maybe we can have an alternative brick that defines a different lighting conditions. NPCs could be, once again, in a different bricks. And if for whatever reason we want to do a bonus mission in which the screen has been broken or completely destroyed, we can have a bricks on top that actually is removing some of the geometry, some of the setup from the bricks below. And so that's the way we basically do a bonus mission for the Hitman game. And if you want more details about the bricks, which is a very powerful system, I can recommend this GDC talk from one of my engineers. Finally, we're pretty happy with the tech. Of course, there are always things that can be made better. So this is a brief list of some of the major things that we're planning to to rework or improve moving forward. In particular, I'd love to cover the top two because I think one of the biggest mistake we did originally was designing the asset system around the concept of files on disk, which I think it's a disaster moving forward, especially now that content for games is growing and growing and growing. And when you throw in procedural generation, suddenly you don't even have files on disks anymore, right? So what we're trying to do there is moving towards more high-level concept, you could say, databases, data streams, stuff like that. For instance, I've showed that most of our resource IDs, they're basically file path, right? They're pointing to something on disk, which is also in perforce, and that is causing us a lot of troubles when, when it comes to renaming or trying to, moving things around in the hierarchy. Luckily, we have an asset database with metadata and stuff like that, so we can kind of work around that. But I think that was a big mistake originally. Another thing that is something we have been working recently is visualizing the version control. So a big chunk of your daily time is basically spent by going to your machine, syncing the entire assembly folder, and then you start to work. And you're syncing, again, 600 gigabytes of data, and you will probably only need a tiny subset of this. even more, actually, the way our asset system works is that the cache is generally almost always warm. So most of the time, you're not even reading those assets. All you really need is basically just the MD5 of those assets. So what we have been prototyping is a system that completely abstracts away perforce, where you can do an instant sync, basically. You can just say, OK, now I'm on this change list. And from the file system point of view, suddenly all those files have changed. They don't really need to be physically on your machine. And the thing you care about is that you can very quickly query those files for their MD5s without even fetching their actual content. Other things we want to embrace is fully distributed cooking. So as I've described, basically each machine running G2 is participating in the packing process. The fact that we send everything to a distributed cache kind of distributes the load between the user. But the reality is also, if you are an artist that are changing more things more often, you pay a bigger price. So we want to basically move to distributed packing. So the ability of just asking a bunch of build robots, hey, can you pack this for me? And the global metadata database is also something we've started looking into. As I mentioned before, each resource server knows everything about your resources locally. But what we're trying to introduce is basically it's a global database that collects information from all the resource servers around and can basically allow you to do searches not just on a specific snapshot of the data, but searching through the entire history of the project and how assets have changed and so forth. And and entities as well. We're pretty happy with entities. They're pretty flexible. There's a bunch of additional things, mostly usability improvements on the editor side that we would love to do. So supporting multiple words to be running concurrently. That's the usual battle against singletons and that kind of anti-patterns. Supporting multiple views, which is something we lack, and we are open to the idea of additionally supporting some kind of scripting, textual scripting language, right? So entities are pretty much a visual scripting language, but sometimes designers, they would love to, be able to type a one-liner to do math instead of doing math through boxes and things like that. And that's pretty much it.